Uh, if when we have when we have calculated the all the cut-off frequency due to the each capacitor, so and then after that we can determine the actual low cut-off frequency. So by choosing the highest value among the calculated values. So and then after that we can plot the Bode plot. We can do the Bode plotting. So in the Bode plotting, the after you draw the axis, x-axis should be in log scale for the frequency, and then y-axis is again in a linear scale. So in the frequency axis, put the you can label the every frequency. So we have, for example, in the previous example, we calculated cut off cut off frequency from three capacitor. So we have three frequency value. So we can label these three frequency value in the frequency axis. Okay, so in the Bode plot, so above the highest calculated cutoff frequency, it is the midband. So the midband, ideally, for the midband, the gain will be at the fixed value. So the midband level is at the fixed value, and then after it reached the highest calculated cutoff value, so we consider as actual low cutoff frequency, so the gain will decrease. Okay, so if you see this graph, we have a dashed line here, and then we have the blue line. So the blue line is this one is the blue line. This is the actual Bode plot curve, and then this dashed line is our approximate or our simplified Bode plotting. So in this course, if you are asked to draw the Bode plot, so we will draw this dashed line. Okay. So the blue line is the actual where we apply the smoothing. To smooth we will have some curve here, so it will be more realistic, or will more near to close to the what is the actual measured or actual observed Bode plot for the BJT. Okay, so beside of the cut-off frequency, we also have a term what we call it roll-off. So this roll-off, what is roll-off? Roll-off is the amount of attenuation. Attenuation means the loss in gain at this frequency. So the roll-off indicate how fast the reduction of or the decrease of the gain over the frequency. So if the roll-off is high, so means that the frequency decrease rapidly. If the roll-off is low, so that means that the gain decrease gradually. So the roll-off is described as dB loss per octave or dB loss per decade. So here, so as I mentioned, the roll-off is dB per decade or dB per octave. So the roll-off is the reduction, the how much the gain reduced at certain frequency range. So this one is gain, and then the decade is the frequency range, frequency change. Okay, so in the frequency we can the frequency changes we can use whether decade or octave. So what is dB per decade? So okay, then take note that we'll put minus here. So this minus minus symbol or minus symbol here indicate the reduction. So because usually the dB we don't have any the dB the unit for the gain in dB is is a log value, so we'll put this minus here to indicate the reduction. So minus dB per decade. So the term decade here refer to the changes of tenfold changes. So tenfold changes is for example from 10 Hz to 100 Hz. So this is tenfold change, or 1 Hz to 0.1 Hz. This is also a tenfold change. So the 10 Hz to 10 Hz, so 10 Hz to 100 Hz is multiplied by 10, and then 1 Hz to 0.1 Hz is divided by 10. So this is tenfold change. Okay, so minus dB per decade is how much the gain decrease in dB unit for every tenfold change in frequency. Okay, for attenuation at low frequency end, it refers to the loss in gain from lower cutoff frequency to a frequency that is one-tenth the cutoff value. Okay, for this example, let's say the FLS is 6 kilohertz and the gain is 0 dB. The gain is 0 dB, and then FLS is 9. So this is 9 kilohertz. Oh, see 9 kilohertz. This is not here. This is kilo, should be okay. Sorry. This graph does not show this example. So let's consider this statement. So FLS is 9 kilohertz gain, 9 kilohertz frequency, and the gain is 0 dB. Okay, the gain is 0 dB. So if the roll off is minus 20 dB per decade, so means that let's say I put this frequency is 9 kilohertz and then gain is 0 dB. So if the roll off is minus 20 dB per decade, so means that when the frequency is 0.9k hertz, so the gain will be minus 20 dB. Okay, so if the frequency is 0.09 kilohertz, so okay, if the frequency is 0.09 hertz, so it will come minus 40 dB. So this is how you can calculate, how you can determine the gain if the roll off is given. Okay, if the roll off is given. Okay, so for one capacitor, circuit, so the roll off is minus 20 dB per decade. Okay, instead of using the dB per decade, we can use dB per octave. So dB per octave is referring to the twofold change in frequency. Twofold change in frequency. So means that if the frequency is the initial frequency is 10 Hz, so the twofold change increment is 20 Hz. If the initial frequency is 10 Hz, the twofold reduction is 5 Hz. So 10, the upper one is 10 times 2, and then the lower one is 10 divided by 2. So this is change of twofold. Okay. Okay, so for the attenuation is referring to the loss in gain from the lower cutoff frequency to a frequency 1/2 the cutoff frequency. Okay, for example, if the FLS is 9 kilohertz, the gain is 0. Okay, if the roll off is 6 dB per minus 6 dB per octave, so means that at frequency of let's say 4.5, because 9 divided by 2 is 4.5 kilohertz, the gain will be minus 6 dB, because the roll off is minus dB per decade. Okay. Okay, so for one capacitor, this is 6 dB per octave. Okay, roughly the 6 dB per octave is equal to 20 dB per decade. So you can use either 6 dB per octave or 20 dB per decade. So which one, either one, you can use either one. Okay. So this is the Bode plot showing the roll off. So in the previous example, we have three capacitors in the circuit. We have two coupling and then we have one bypass. Let's say we have here is the bypass, and then this is input and then output coupling. So this referring to the bypass capacitor, the free cutoff frequency due to the bypass capacitor will become the low cutoff frequency because it is the highest value. And then after that, the reduction of the gain will be the rate of reduction will be 20 dB per decade, or minus 6 dB per octave. So this is minus 20 dB per decade or minus 6 dB per octave. Okay, so because of at this point there is only one capacitor CE appear. Okay, so what happened above the FLCE, this is a mid band. This is a mid band. In the mid band, there is no capacitor because this is a short circuit. Okay, so once the frequency change towards the lower frequency, and then it reach the FLCE, so the CE appear in the equivalent circuit. So in this equivalent circuit, only one CE appears, so this is 20 dB per decade or 6 dB per octave. Okay, after that, if the frequency reach the second frequency, FLC1, so we have two. So in this region, we have two capacitors. So one is C1 and then we have the CE. So because we have two capacitors, the rate of reduction or the roll off is become double. So we have 20 dB per decade or 12 dB per octave. Okay, after it reached the last cutoff frequency, so all the capacitor appear in the equivalent circuit. So we have here C1, we have C2, and then we have the CE. So because we have three capacitors, the roll off is triple. So we have 20 times 3, so 60 dB per decade, or 6 times 3, 18 dB per octave. So this is how you can draw the Bode plot at the low frequency.